Okay, these notes are going to help us take a look at our equilibrium reactions. This is our intro notes for our unit. If you were missed class or just need a review on this will help with the equilibrium expressions as well. All right, so chemical reactions typically happen in one direction, reactants forming products. Examining the activation energy of a one-directional reaction, it's possible to reverse reactions can help see why a reaction is reversible. So by examining the activation energy of a reaction, we can see why a reverse reaction can happen. The one-direction reaction pictured in the graph below shows the activation energy of both the forward and reverse reactions. So, number one, it says label the reactants and products on the graph. So our reactants always start on the left, so we'll put R for reactants. And our products are always at the end of our curve there, so products on the right. Okay, so whatever, we can think of our reaction as R forming P. Okay. Number two says label the activation energy of the forward reaction as EAF. So to go from the reactants to the products, we have to first go over this hill. So the amount from that we start with to the top of the hill would be our energy of activation, and that's for the forward reaction. So we're going to put an F there. Okay, activation energy of the forward reaction. It also says and label the activation energy of the reverse reaction. So our reverse reaction would be if the products could form back into the reactants. We're going to go the other way. So if our products form back into the reactants, we would have to get over this hill. So starting down here and going all the way to the top, this other arrow and difference would be our activation energy of our products, or excuse me, of the reverse reaction. Put EAR. So activation energy of the reverse. So we've got one going this way and the other for the reverse reaction. Now we're going to do some comparison. So how did the two activation energies compare to one another? So hopefully we can see that our activation energy of our forward reaction is much smaller than the energy of the reverse reaction. So activation energy of the forward is much smaller than the energy of activation of the reverse. Okay, so how does the difference in activation energies explain why the reaction only takes place in one direction? So this reaction that's represented by this graph is not reversible. It really only goes from reactants to products. So this difference in activation energies explains why. It is much harder, as in it takes more energy, to reverse the reaction. And make more reactants. Okay, we have a much larger barrier. So if you think about it, you're riding a bike and you have to go over a hill, but the first part is kind of a little hill, but when you get to the top, you're like going way further down, like into a valley. It's going to be much harder to go the other way to get back to where you started. Much more energy. So underneath it says reactions in equilibrium proceed in both the forward and reverse directions at the same time. So one direction and the other direction would be happening at the same time. The amount of energy required for either direction are not the same, but there is not a large difference between the two. So that's what makes a reversible reaction possible, is that this difference is much smaller between the two. Okay? As the amounts of reactants and products change, it affects the rate of each of the reactions. It's going to affect the speed. When the reactions are occurring at the same rate or speed, they reach a state of equilibrium. Okay? So when our forward and our reverse can happen at the same speed, we get that equilibrium. Chemical equilibrium is a state in which the forward and reverse reactions are occurring at the same time and at the same rate, and there is no change in the concentrations of reactants and products overall. So they're both occurring, but we're not changing their amounts of chemicals. From a macroscopic view, so what we see with our eyes, we would not see any change in the chemicals in the reaction being observed. On an atomic level, if we could zoom in, we would observe the forward and reverse reactions occurring simultaneously as the reactions continue to occur. So reactants are forming products, products are forming reactants, but they're happening at the same speed, so your overall change is not, there's nothing happening there. So an example of that, and we're going to use this chemical in a demo that you guys are going to watch for your next part. This is a purple solution. It's actually a reversible reaction that's occurring inside the solution. But you can see there's no color change happening. It just looks purple. So this means that the amount of products and reactants isn't changing, so our concentrations of them are changing, but our overall concentration isn't changing, but at the microscopic level, there is a reaction occurring at the same speed, forward and reverse. Okay. All right, so we can analyze reaction graphs and observe the changes in concentration of the reactants and products over time as they reach equilibrium. Answer the questions that follow the two graphs for this reaction. So this is our reaction that we're going to be analyzing here. If you've got some highlighters, pause this and grab them out. You'll want some highlighters or colored pencils to help you, something there. So it says number 5 down here. First thing we're going to do is highlight each of the chemical lines in a different color and create a key here. So we've got our SO2. I'm going to do that in blue. So all of my SO2 lines I'm going to do in blue. And then I'm also going to go ahead and highlight this so it's easy to find. And then I'm going to do, I'll do green for oxygen. All my oxygen lines. And we'll do pink. Why not? So pink for our SO3. Alright, so now it's going to be easier to kind of match things up because we've got a lot of chemicals going on here. So it says fill out the table below with the concentrations of each chemical at each time in the reaction. So our times are shown here as A, B, C, and D. They're not specific times in seconds, but they're just reference points for us to kind of just see what's happening. So we're going to start with the SO2 of our first graph. So at time A, at the beginning, we have 2.0 into concentration, so we could say molar for everything. At time B, we've got a little more than 1, I'd say like 1.1. At time C, we're at that 1.0, and at time D, we're also there. Okay. Same thing with O2. So O2 starts at 1 molar. It's going to drop down when we get to B. It's almost at that 0.5. I'd say like 0.6. Time C, we're definitely at that 0.5. Time D, still at that 0.5. And then our last one, SO3. So you can always pause and kind of do this on your own and try it out. But at time 0, we've got 0, because it's right at the beginning. At point B, we're pretty much equal with that blue line. So the blue line was at 1.1. At time C, we're at about 1.25, looks like. And still at that at D. All right. Let's do the same thing over here. So SO2 is starting at 0. So is our oxygen. Okay. Oxygen, or the SO2 is increasing probably to about 0.9. And then by C and D, it's at 1.0. Oxygen starting at 0, probably to about 0.4. And then to that 0.5 mark for the rest. and then SO3 starting at 2, dropping down to about 1.4, and then dropping in between like 1.25, looks like. All right, and again, these are estimates, so we just need some comparison data. So overall, we can see that our amount of SO2 were decreasing over time in this first reaction. Our O2 is decreasing, and our SO3 is increasing. So according to our reaction, we started with amounts of reactants, and we formed the products. So we're starting with amounts of reactants, start with no product, and increase our product, decreased our reactants. In our second one, we started with product, so we're starting with more of this chemical and no reactants. So that's going to force the reaction to go the other direction, and we're going to make more of the reactants and use up some of the product. So it's kind of shifting a different direction in this case. So on the back side of your paper, we're going to look at the questions that go along with this. I think I have one for the back side. All right. So let me get blank. All right. Just getting set up here. So I've got our questions here. So you can kind of I'll keep the graphs up on mine with the data, and you can flip to the other side so we can see both of them. So our first question is, what happens to the amount of reactants in graph A? So our reactants are SO2 and O2. We can see that their amounts are decreasing over time, decrease. Number 8 says, what happens to the amount of products in graph A? Our product SO3 is increasing, so it increases. Number 9, how is the initial amounts of chemicals different in graph B than graph A? So in graph B, our initial amounts were starting with product and no reactants, where in graph A, we started with reactants and no product. So they're opposites. So no reactants, only products in B. Okay. So at what time does the concentration of each reaction graph reach equilibrium? So we can see equilibrium is reached on both graphs. And you can see that it's when our lines really flatten out. This line could have probably been scooted over a little bit. They're being a little conservative on that, but in graph A, it reached equilibrium at point D, and in graph B, it reached it at point C. So graph A reached it at point D, graph B, it reached it at point C. So it says compare the amounts of each chemical at equilibrium for each graph. So our comparison, when we get to equilibrium, so these 2 points are the same at equilibrium for, or the bottom one is, and it's equal or the same as graph D. So their amounts are the same. Okay, so what this means is that no matter what chemicals we start with, we're going to end up with this similar amounts or similar ratio of one chemical to another. In this particular example, it had the exact same amounts to kind of drive that point home, but really it's the same ratio of chemicals, of reactants and products when we reach equilibrium. So what we're going to set up is something called an equilibrium expression, and that is simply a ratio to express these amounts of chemicals. All right. So it says equilibrium expressed through an equilibrium expression and an equilibrium constant. The equilibrium expression for the reaction. So if this is our example reaction, we've got coefficients as lowercase letters, and the chemical, oh, my hand is in the way, the chemical is the uppercase letters. Okay, so if this is our example reaction, the equilibrium expression is this equation here. So it's capital K And the little EQ just stands for equilibrium. So this is our equilibrium constant for this. And notice we've got C and D on the top. So we've got our product chemicals on the top. They have brackets around each one that represents concentration. So we'd be putting in things like molarity here. And then they have an exponent. Our exponent is going to come from the coefficient here. We're dividing it by the reactants, and again, they're being raised to an exponent of their coefficient. So we're going to write the equilibrium expression for the reaction in the previous graph. So our reaction in those graphs, just to kind of rewrite it here, is 2SO2 plus O2 forms 2SO3. So we want to transform this reaction equation into an equilibrium expression. So we start with KEQ. We're going to start with products on the top. So our first product here is SO3, so concentration of SO3. Its coefficient is 2, so it's going to be squared. We're going to divide that, since we have no other products, by our reactants. So concentration of SO2, its coefficient is 2, so it's squared, times the concentration of O2. Its coefficient is 1, so it's raised to the first power. Okay. So this is its equilibrium expression. It's just an equation that we can set up, but it's a really nice starting place for any equilibrium situation to go ahead and just write its equilibrium expression. So you remember that you have an equation that you can always fall back on to try and find information about the reaction. It's kind of like in our last unit with rate laws, where we always just wrote the rate law at the beginning, so we had it to refer to. Number 13 says to calculate the equilibrium constant for the reaction in graph A. So this constant is based off of the ratio of these chemicals to each other when the reaction is at equilibrium. So the only concentrations we could put in here from our table on the front would be the ones where it has reached equilibrium. So for graph A, it would be at time D, and for graph B, it would be at time C or D, okay, because they've reached equilibrium. So we're going to go ahead and calculate our equilibrium constant. We're going to place the values in for this, and it says for graph A. So for graph A, we want all the values at time D. So our value for SO3 was 1.25 molar. We're going to be squaring that. SO2 is 1.0 molar. We're going to square that. And then our concentration of oxygen is 0.5 and probably 0.5, 0 to be safe here. We do have another significant figure, and that's raised to the first power. So we're going to go ahead and calculate this. I'll show you guys how I put it into my calculator. So we've got, I do 1.25 squared in parentheses. I'm going to go ahead and divide that. 1 squared is just 1, times 0.5 is 0.5, so I'm going to divide that by 0.5. And my equilibrium constant is probably got 2 sig-figs here, so 3.1. Now, fun part about this, if you notice, we've got molarities and all kinds of different units. Depending on these exponents, it's going to change how many molarities we have there. The deal with units on this is that there are no units. Equilibrium constants have no units on them. So if we're reporting our answer, we want to show how this is equal to each other somehow, or you can do KEQ equals 3.1 to show like your final answer, so it's very clear. All right. 14, is the equilibrium constant different for the reaction in graph B? Explain why. So if we look at the reaction in graph B, all of our values at equilibrium are the same as graph A. So our equilibrium constant would be the same as graph A. Because the values are the same at equilibrium. Okay? Now, it could also be that they're a little bit different values, but that when we plug them in, they're the same ratio of chemicals. So that's another way we could have the same equilibrium constant. So what does our equilibrium constant tell us? The value of our equilibrium constant can tell us which side of the reaction is favored in a reaction, to show us which chemicals are present in higher concentrations at equilibrium. So when our equilibrium constant is greater than 1, it means that more products are present. Because if we think about this setup, if this fraction is products over reactants, if this value we get is more than 1, that means we have a higher numerator, which means we have more products. So our products would be favored. We have a larger numerator. Okay. If KEQ is less than 1, it means more reactants are present. At equilibrium, we have more reactants present. We have a larger denominator, which means our reactants are favored. So at equilibrium, we'll see that we have more reactants in the higher concentration. If it's equal to 1, that just means that it's like that our concentration of our reactants products are equal to each other at equilibrium. So the ratio of reactants to products is equal. It's a 1-to-1 ratio. So we're going to take a look at writing some equilibrium expressions and doing some calculations. I'll talk about some things we might run into in our practice and some notation that we should be aware of. So, let's use this as well. So for our equilibrium constant up here, it's greater than 1. So that would mean that more products are present at equilibrium. We can see that in our graphs. Our product is SO3. The amount of products we have is greater than our amount of reactants. So that ratio is greater. So our equilibrium constant is greater than 1. We could say that products are favored. Okay. So number 15, we want to write our equilibrium expression for this reaction. So KQ equals, we've got our products on the top, so NH3, we're going to square that because of its coefficient, over nitrogen and hydrogen. We're going to cube the hydrogen because of its coefficient of 3, and 2 would be raised to the first power. We don't really have to write the 1. So this is our equilibrium expression. Do not forget to write the left side of your equation, okay? All right, number 16, what is the equilibrium constant when nitrogen is 3 molar, hydrogen is 1.5, and ammonia is 0.01? So we just need to plug these values into our expression and solve it. So we've got NH3 is 0.010. Since our units don't really matter, I'm just going to leave them out for this. It's kind of awkward. Drill that all year to write units, and then this is where it's okay to not. Hydrogen 1.5, and we're cubing that. Okay, so we've plugged in all our numbers with our exponents. Now we're just going to solve. So I've got 0.01 squared. Gives me that. I'm going to go ahead and divide that by 3. Gives me that, and then divide it by 1.5 to the third power. And I get that. Now that's a ridiculous number. We're not going to leave that like that. Put it in scientific notation. So we get 9, see we've got 2 sig figs. So 9.9 times 10 to the -6. Okay, don't forget to write your exponent part over here. I've had some numbers lately in scientific notation on tests and things. You guys are leaving off the important part, exponent. All right, so that's our equilibrium constant. So let's look at it. Does it favor the reactants or products? So this value, if we think about this negative before we had it in scientific notation, much smaller number. So this is much less than 1. KEQ is less than 1. So that means more reactants are present. So we have that the reactants are favored. All right, now here's one little exemption from this whole thing. It says pure solids and liquids are not included in the equilibrium expression. This is because they do not affect the reactant amount at equilibrium in the reaction. So they are disregarded. So if you have a pure solid or a pure liquid, they do not have a concentration. This carbon is a solid. That solid does not have a concentration like a molarity or an amount. So it is left out of the expression. So if we were to write this expression, we'd have our products. So we've got H2 gas times CO. Coefficients are 1 on each of them. And we've got H2O. And then we're going to leave out the carbon. Now, it doesn't mean that it's not important to the reaction. It just means it's not going to affect the equilibrium. We could add or subtract any amount of carbon we want from this reaction, and it's still going to be the same equilibrium. Okay, so then our constant with these values, we've got hydrogen is 2.5 times carbon monoxide is 1.5 divided by 2.00. Calculate that. 2.5 times 1.5 divided by 2. 1.875. We've got 3 sig figs on everything, so 1.88. It's our equilibrium constant. All right, are the reactants or products favored? We've got a value that is greater than 1. Products are favored. What that means is that this top number is larger overall than this bottom number. Okay? We have more products overall than we have reactants. Okay, here's the last thing we're going to talk about that you'll see represented in your practice, or 2 things. Number 1 is some of the possible things that we can have listed here. So our equilibrium constant is actually just K. We have different subscripts that we add to it that give it clarity on what kind of equilibrium we're looking at. So KEQ is like the generic one. It could apply to anything. But you could be asked for something like KP. And what that means is that it's in terms of pressure. So it's for pressures. We're going to see how that one's a little bit different. We could be given Ka, and that's for acids. So we're going to be exploring acids and bases here. So you might guess that Kb is for bases. And the last one you might see is KSP. And what that stands for is the Solubility Product. Okay, and what that really is just looking at is it's for dissolved salts. Okay, so I'm going to show you guys on your practice a couple of examples of where you will see these. Okay, and we're going to set up something just slightly differently for the pressure one, just to show it in terms of pressure. Everything else is going to look just like these. Okay, it's just we label it differently according to what chemicals we've actually plugged in. So for this top part, you can just write, you're writing your equilibrium expressions. You can just use KEQ, it's fine. For the next part, it's going to be more specific. So for instance, this one says KEQ, KEQ. This one says Ka because it happens to be showing an acid. It's not going to change your setup, you're just going to label it differently. This one's Kb because it happens to be showing a base. Again, just labeled different. KSP, Again, just labeled different. But with solubility product, the interesting thing here is that it's always a solid that's dissolving, and your pure solids are not included in the expression. So you only end up with a top part of your fraction for KEQ. Okay, so if we think about, where was it? Where was it? On the other page. If we think about it as products of reactants, if our reactant is always a solid and not included, then it's just the products. That's why it's called the solubility product. Okay, gives you a little hint there. So those ones are pretty straightforward. On the back, it deals with pressure. So I'm going to show you guys one of these so you have an example going forward. So it says, write each of the following 10 through 12 equilibrium expressions in terms of partial pressures. Then calculate the equilibrium constant and determine the products or reactants are favored. So similar setup, but it's in terms of pressure. So all that does is we're going to label things a little differently. Notice how we're given these. It says pressure of NH3, pressure of O2, pressure of N2, pressure of H2O. So it's not given as a concentration in brackets like the previous ones were. So we're going to express it in terms of pressures. So it's still products over reactants. So I'm going to start on my product side. But I'm going to write it in terms of pressure. So I'm going to put pressure of N2, and I'm going to raise it to the second power. I'm going to multiply it by the pressure of water. You can just use regular parentheses here because brackets show concentration. This is to the sixth power. We're going to divide by our reactants, so pressure of NH3 to the fourth power times your pressure of O2 to the third power. So again, same setup, still products over reactants, but now we can actually put these pressures in, partial pressures. Again, you won't have any units on this. So anytime we see Kp, it's just, again, in terms of pressure. One other thing I'll point out is on our equation sheet, you are given, let's see if I can zoom a little here. Nope, it's off. Okay, do it manually. So you guys can see that you're given kind of this generic equilibrium expression, and it also shows it in terms of pressure, shows it in terms of an acid and a base. So we've kind of got the different forms of the equilibrium expression here as well, the generic ones. We'll learn the rest of these equations pretty soon. They're not too bad. Okay? So that's in terms of pressure. Again, you plug your values in, and then it being less than or greater than 1 will tell you if it's product or reactant favored. Okay? All right, I think we're good. Try out that practice, and again, put a question mark next to specific ones you don't understand. Write a question so we know what we need to go over when we get back.